Next, we look at such an equation. We won't waste time on the first process, and we write its characteristic equation directly. That is, lambda squared plus 2 lambda plus 1 equals 0. It's easy to know that lambda plus 1 squared equals 0. Its characteristic roots are lambda 1 and lambda 2 equals minus 1. In this case, of course, we know that a times e to the power of minus t is one of its solutions, but the solution of the second order ODE needs two initial conditions, which are the value of x0, 0 and the value of dx dt when t2 equal to 0. So we need another general solution with underdetermined coefficients. According to the current conditions, we know that e to the power of minus t must meet the equation. We might as well take a look at t times e to the power of minus t. We derive it. It can be written as e to the power of minus t times e to the power of minus t. The second derivation of it can be written as minus t e to the power of minus t minus e to the power of minus t plus t times e to the power of minus t. Substitute the three expressions into the equation and reorganize it. It can be written as this is the second derivation. This is the first derivation, and this is itself. Look, these two are eliminated. These three are eliminated. So it is equal to 0. So we prove that t times e to the power of minus t is also a general solution of the equation. Thus, for this case with repeated roots, the form of its general solution is that x equals a times e to the power of minus t plus b times t times e to the power of minus t. Here we look at this situation. Its characteristic equation is lambda squared plus 2 lambda plus 2 equals 0. Because delta equals b squared minus 4ac equals 4 minus 8 equals minus 4, which is less than 0, it must have two conjugate complex roots. We can also use the method of completing the square to write, that is lambda plus 1 squared plus 1 equals 0. So the two conjugate complex roots can be written as lambda 1, 2 equals minus 1 plus minus j. Please note that we usually use the letter I to express an imaginary number in high school, that I equals the square root of minus 1. But in circuits, because we have used the letter I to express the current, so we use the letter J to express the imaginary number. So for the equation, it has two conjugate complex roots. We know that a times e to the power of minus 1 plus j times t plus b times e to the power of minus 1 minus j times t must be the general solution of the equation. But this expression is too complicated. We might as well use Euler's formula to simplify it. It can be written as e to the power of minus t times a times cosine t plus j sine t plus b times cosine t minus j sine t. Reorganize it as e to the power of minus t times a cosine t plus b cosine t plus j a sine t minus b sine t. This is a very complex expression also, and still not convenient for application. But we found that it's a complex expression. If the complex expression wants to meet the second order ordinary differential equation, its real part and the imaginary part needs to be okay respectively. Now let's verify it. Is e to the power of minus t times cosine t a solution of the equation? We find its derivation. It is equal to minus e to the power of minus t times cosine t minus e to the power of minus t times sine t. Its second derivation can be written as e to the power of minus t times cosine t plus e to the power of minus t times sine t plus e to the power of minus t times sine t minus e to the power of minus t times cosine t. So it's equal to 2 times e to the power of minus t times sine t. Substitute the two results into the equation. We know that e to the power of minus t cosine t is a solution of the equation. Similarly, e to the power of minus t times sine t is also a solution of the equation. So we can write the general solution of the equation with two conjugate complex roots as a form of x equals a times e to the power of minus t cosine t plus b times e to the power of minus t times sine t. Of course, we can also use the triangle identical transformation to write it as a form of k times e to the power of minus t times sine t plus theta. A and b in the former expressions are underdetermined coefficients, and k and theta in the later expression underdetermined coefficients. These two expressions are equivalent. Through previous study, we know that for second-order linear ODE with constant coefficients, its solution may have three possible forms. That is, different real roots, same real roots, and conjugate complex roots. Their corresponding expression of the general solution are different. This result is very important for learning the second-order circuits.